Okay, so our next speaker is Cris Hasan from the University of Glasgow, the Adam Smith Business School, and he's going to be talking today about multi-objective optimization for sustainable transitions. So whenever you're ready, thank you.
Thank you, Oliver. Thank you for inviting me to the conference. I've been enjoying a range of very interesting talks. So today I will, can you hear me well?
Yep.
Yeah. Today I will introduce a multi-objective optimization model that we have developed to sort of balance out social and environmental targets, and explore how this model can be informed using machine learning and text mining techniques. So to provide some context, let me introduce you to Gallant, which is a partnership between the University of Glasgow and Glasgow City Council. Our research consortium is funded by the Natural Environment Research Council over the span of 5 years. And the overarching goal of the project is to sort of help the city achieve a just and sustainable transition. So what exactly do we mean by a just and sustainable transition? Well, one way to sort of try to understand this concept is through the framework of donut economics. So this framework suggests that we need to meet the essential human needs defined by the so-called social foundation represented in the inner ring of the donut, without overshooting the so-called ecological ceiling depicted by the outer ring of the donut. So in order to remain within that sweet spot in the middle ring of the donut, we need a healthy balance between sustaining social targets and sort of pursuing environmental outcomes. But the challenge is twofold. First, social and environmental targets are often in conflict with each other. And second, policies and interventions are commonly planned in isolation, failing to account for complex interdependencies and negative unintended consequences. So this talk will be divided into two main parts. The first part focuses on a multi-objective optimization for social and environmental targets. And in the second part, I will introduce a text mining approach supported by a novel machine learning algorithm in order to inform this optimization model. So in the first part, I will introduce a modeling framework that performs a multi-objective optimization for reconciling social and environmental targets. So the general idea of the framework is to analyze the impact of different policies on targets. And we also aim to capture the intricate interdependencies within policy target networks. So our framework, it's a bit funny. The font doesn't appear very well. So this is supposed to be E with some subscripts representing the edges between policies and targets. So our framework will be in the form of a multi-objective optimization model that employs a dynamic evolutionary algorithm performed in conjunction with network analysis. So this is the setup for our policy target network. We define a two-mode network where the nodes are divided into two disjoint sets representing policies and targets. And then the unidirectional links from policies to targets represent or signify the directed impact of policies on targets. And then each edge is assigned a link coefficient, where the sign of each coefficient can be either positive or negative, indicating whether the impact is beneficial or detrimental. And the magnitude of that coefficient quantifies the weight or the strength of that impact. So to configure our policy target network, we start by generating a sequence or an array of policy outdegrees, which represent the directed edges from policies to targets. And then for each edge, we randomly assign a link coefficient, which is also generated from some randomly generated random variable. Those two random variables are random arrays of random variables are generated using two types of probability distributions. The first one is the beta distribution, which is used to generate discrete variables. And the second is beta binomial distribution for continuous variables. And then the underlying parameters mu and beta represent the average and scale of these distributions, allowing for the fine-tuning of the underlying network topology. To this end, we can select the appropriate parameter values of the underlying statistical distributions, which allows us to experiment with different network topologies and capture a range of hypothetical scenarios. In this matrix representation, each cell represents the direct influence of policies on targets, quantified by the link coefficient in the respective cells in the interaction matrix. So the general idea of multi-objective optimization models is to find a solution that optimally reconciles conflicting objectives, or in our case, conflicting targets. So for our purposes, we use an evolutionary algorithm called the NK-fitness landscape. In this algorithm, we define a policy configuration X, which is a numerical array representing how resources are distributed among the policies. And then we impose a resource constraint that signifies how policies are limited to the availability of resources. Then each target within the network is characterized by an individual performance function or an objective function, which we need to optimize. In addition to that, each target is assigned a relative importance weight ranking, representing its ranking in a priority list. And the overall performance for each policy configuration is calculated as the weighted sum of all individual performance functions. And then at each optimization step, we search for policy configurations that maximize the performance while navigating the adjacent neighbors and adhering to the resource constraint. So here we can visualize the multidimensional performance landscape, which illustrates a set of interconnected policy configurations and their corresponding performance levels. So each policy configuration is visualized as a vertex, and the vertices are colored according to their overall performance, depicting their sort of elevation in the landscape. And the dashed diagonal line represents the constraint boundary that we cannot go beyond. So there's an availability of resources that restrict our landscape in that sense. So by navigating this performance landscape, we can search for the most sort of promising policy configurations while adhering to the availability of resources. So gamma 1 and gamma 2 are two trajectories that follow the optimization algorithm. So you start from sort of like a very low performance node, and then you hill climb to the local optimum. So sensitivity analysis is a technique that try to understand how changes in parameter affect the overall output of the system. In this analysis, we focus on three crucial parameters: the budget, network interconnectivity, and overall efficiency. I will not go into the details of these findings, but I will make the following general conclusions. First, the qualitative behavior of the system is robust to perturbations, meaning that small changes in parameter has no significant impact on the system performance. And second, the quantitative behavior is primarily determined by two parameters: the budget parameter and the overall efficiency. So we were able to draw these general conclusions with the caveat of the importance to support and validate these findings with real data. So the next step may involve informing the model with available data in order to provide evidence-based insights. And that brings us to part 2 of the presentation, where I will introduce a text mining approach powered by machine learning techniques in order to inform our optimization model. So one of the primary challenges is processing and analyzing vast volumes of documents, which involves dealing with a diverse sources of data, which is a very difficult and time-consuming task. Not to mention that integrating such diverse set of data requires a deep understanding of various contexts and nuances. So one may suggest large language models, which are very powerful tools, but they do come with notable limitations. First of all, large language models don't have access to specialized knowledge bases, which means that they may generate generic responses and lack depth in their responses. Language models also can suffer from a phenomenon known as hallucination, where the model generates an inconsistent, inaccurate, or even completely incorrect outputs. LLMs also tend to be outdated, as they're not being regularly trained on a regular basis. They also fail to support traceability or citability, making the information less credible. And even when supporting these models with auxiliary data, they do struggle with integrating large amounts of new training data. One alternative is fine-tuning, but that's also computationally expensive, not to mention that it could lead to overfitting. So to overcome these challenges of traditional large language models, we utilize an emergent approach called retrieval augmented generation, which aim to retrieve relevant information from an auxiliary knowledge database and augment it to an existent language model. So we can use our own content, for example, our own library of documents, and augment it to our language model. So powered by vector embeddings, these models can be can provide a fast and efficient method for contextualizing the data that are flowed into the model, which I will explain in a couple of slides. We also utilize some of the open source libraries like LangChain and Llama Index, which apply principles from RAG and combine specialized LLMs for different tasks. So RAG offers several significant advantages over traditional methods. First, it takes existing capabilities of large language models and extend them to specific domains and niches. Also, it enables us to build our own curated knowledge to provide context to the models. So RAG developers often use the analogy of open book versus closed book exams, but I will take this even further and liken RAG to a student who not only got access to an open book, but someone who had prepared written notes or a cheat sheet the night before the exam. RAG also supports citability and traceability from original data, making the context preserved and well represented in the output. And more importantly, instead of hallucinating, the system would recognize instances where no information is provided from the context and admit that we don't have this information. RAG also circumvents privacy and copyright issues. And finally, it's a dynamic and iterative approach, allowing for a more flexible framework. So at the core of RAG is vector embeddings. It's the concept of vector embedding. So a vector embedding is a numerical representation of data, whether it's text, images, or another raw format. So specifically for textual data, vector embeddings can capture the semantic and syntactic meanings of the data and then store them in a multidimensional store called a vector store or embedding store. So when two words are semantically similar, they will be represented by two coordinates or 2 points that are of close proximity within each other within that space. So based on this concept, we can search for similar entities by measuring their distance using a vector search. This can be done using embedding models, which are specialized machine learning models that transform textual data into vector embeddings. So by utilizing these vector embeddings, we can allow for more nuanced and contextualized data analysis. So here I'm showing a two-phase pipeline for our RAG application. The first phase is data indexing, where we start with importing our own auxiliary databases. For example, a library of documents. Then we split these documents into smaller, manageable segments called chunks. These chunks of data are then transformed into vector embeddings using an embedding model. And in the last step, these vector form data are stored in a vector store or a vector database, which allow for efficient storage and quick retrieval. So in the second phase, we start with formulating a query which carries the specific information we try to seek. This query is then converted to a vector embedding using the same vector model. And once encoded, it can be matched against the entries of the vector store in order to retrieve the most relevant data chunks. These chunks of data are then integrated with the original query to form what is known as a prompt. This prompt is then augmented into the large language model, and the language model processes this prompt and generates an appropriate response. This framework can also be enhanced by adding additional steps like validation, evaluation, synthesis, and further analysis. So here I'm demonstrating a proof of concept illustrating how we can use a RAG application to construct a knowledge map in the form of a policy target network. In this network maps the policy documents shown on the left column to sustainability targets on the right column. So in this prototype, when the user clicks on one of the connections, it triggers the system to provide a concise statement linking the policy actions to the underlying targets. And the context on which these statements are grounded is also highlighted. But I'd have to emphasize that this is still a proof of concept and still need to be further developed. So further development includes, we can, for example, include missing unintended consequences, potential feedback loops, and so on. We can also synthesize this information, but it needs to be done in consultation with a broader group of stakeholders. It is also necessary to follow this with evaluation and validation in order to ensure the robustness of the framework. So in this talk, I introduced a multi-objective optimization model and described how it can be informed using a text mining approach. So by integrating those two work pieces, we aim to provide or develop a decision-making tool that helps us identify synergies and trade-offs within complex policy target networks. And since policies are often developed in isolation, this tool may help us detect gaps, redundancies, and misalignments within this framework. And the tool could also help us identify potential barriers and accelerators in order to inform decision makers to provide better or more informed interventions. And finally, we hope to make compile a database of past and current policies and their impacts on targets in order to provide a foundational step to support decision makers to make more informed interventions. Thank you for listening.
Great, thank you for that talk. Certainly really interesting. New applications of LLMs for me at least, and it's nice to see them being put to productive use.
Thanks.
So maybe you have time for a couple of questions if there's anything from the audience. Yes, certainly. Mansa, could you maybe?
That was really interesting. I wanted to ask what the vector embedding model was that you used and how it integrates with the large language model.
Yeah, so there are various ways to generate vector embeddings. The one I've been using, I've explored different models. There's one provided by OpenAI, another one is by Llama Index, another one by LangChain. I think, yeah.
Is that based on the dictionary of the language that they have?
No, I think there are two separate models. So the language model is completely separate from the vector embedding model. So the idea is that they take a bunch of generic data, or if in certain cases they do take specialized data from a specialized domain and use some unsupervised learning algorithm in order to assign a vector embedding for each words or sentences based on their similarity within certain contexts.
So was it each of the chunks was assigned like one row of vectors and then
yes? So are you asking about how we retrieve the chunks or how the embedding model are?
How the embedding model works with the prompt.
With the prompt, okay. So yeah, so the idea is that we try to retrieve the relevant chunks using the embedding model by measuring the distance between the chunks and the query. So you put the chunks on the side, the relevant chunks on the side, and then you integrate them together again with the query and feed them into the into language model. That makes sense.
I think maybe one more question before we switch over.
Thank you. Most interesting. So the discovery of the network topology seems to be one of the things you're trying to discover. This is the last slide.
Yeah.
Oh, you just did a summary at the end.
At the end.
Yeah. Yeah, so up-to-date database of policy target network. So that's basically identifying what you believe the network to be, the topology of it. But my question relates to the strengths, because it wasn't just simply a network topology, but you had some sort of correlation element. So
one of the outputs of this prototype is how related the policy action to the target, and that also can be done by leveraging the embedding model. So we measure the distance between the two chunks of data, the qualitative data from the policy action and the qualitative data from the targets.
the question in some sense also relates to the idea of hidden variables. So there's a hypothesis here that policy directly impacts these targets, but there are sort of actors, so to speak, outside the policy realm and the target realm. So is there also in this framework and approach where you could identify hidden variables, other actors involved here in this, other network players that are not quite captured there?
Yeah, we should certainly be vigilant of the hidden variables, but we also aim to try to look for missing unintended consequences and also look at the sort of implicit relationships among targets, which can be done in a similar way as well. So there is a lot to add to the framework in that sense.
Okay, thanks. Let's thank the speaker once again.